Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge, Unique Paths 3. So this problem says we get an n by n grid, and each cell can have four different values, one of four different values, 1, 2, 0, or -1. If it's 1, that means it's the starting square, so it's not always 0, 0. It can be somewhere else, it can be here, for example. And for 2, that's the ending square, that's our destination. And there is only one ending one and only one starting position. So only one with value 1 and only one with value 2. And 0 represents an empty square that we can traverse, go through. If you have -1, that means it's an obstacle, so we can't go through it. So for example here, this one, we can't go like this, right? Because there is this obstacle. And we can go in the 4 usual direction, like up, left, right, down. Okay, so those are the rules. Now what do we want to return? We want to calculate the number of different paths such that we basically we want the number of different unique paths such that we walk through every square, every non-obstacle square, we walk through it exactly once. Okay, no more than once. And we want the number of unique paths that have that. So let's take a look, for example, here at this example. We can go from the starting position like this, and then go down, and then go left, go right, go here, and then go down, and then go to the destination. The other way we can do it is go from 0, go down, and then go down again, and then go to here, and then go up, and then go 0, 1, which means go here, and then 0, 2, 0, 3, and then 1, 3, which means here, and then 1, 2, and then down. Okay, so that's a different way of doing it, which is going like this. Okay. But there are only these two paths. Each of them will go through each of these empty square only once. Okay, exactly once. For this problem, it's 4, and you could try it, but that's the idea. Now, how do we solve this? So we have neighbors, right? So you may think, okay, maybe we can try DFS or BFS. But there is this constraint of doing it exactly once. And the other thing is that we can visit a set multiple times, right? Because, for example, here you can see we go to 0. We go 0, 2, and then we go 0, 2 here. So in multiple paths, we can go 2 times. Okay, but we can visit the same cell multiple times in the same path, right? Okay, so how do we solve this? So a couple of constraints we need to pay attention to. One is that we need to visit every cell exactly once in each path, right? So what this means basically is that we need to count the number of empty cells, the number of cells we can go through. We need to count them initially, right? So for example, here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you can think of them either empty or non-obstacle. So we have 11 in this case. And so we need to count them so that when we reach the end, we can check, did we traverse all of them? We can do that either by maintaining a count of the ones we encounter and checking if that equal to 11, or we can do that by passing empty, and each time we traverse one, we decrement it, and when we reach the end, we check if empty is equal to 0, and that would mean we traversed all of them, right? It would be less than 0 if we traverse it a cell multiple times, right? If we traversed all of them in the particular cell multiple times, the empty value would be less than 0. So we would want to increment the number of paths only if this is equal to 0. So that's one observation. The other observation is actually we can do this with just DFS because when we traverse a cell, we don't want to just do one path and stop, right? We want to try multiple. Okay, so we can do something similar to DFS, but more with a backtracking approach, because we want to find multiple ways, right, and count them. Okay, so what we can do is exactly that, do backtracking, and then our stopping condition is only if we reach the end, which is basically here we are told it's value 2, and empty is equal to 0, then we can increment the count of paths. Then we can increment our paths to be +1, right? And the rest is pretty much similar to what we usually do with DFS. So we call our DFS function, we go through the neighbors, which are going up, left, right, down, right? And so we will go through each neighbor and then call recursively. But the only thing we need to pay attention to is that, so initially these values are 0, right? 0, 0, 0, 0, 0, 0. So within a single path, to not do something like maybe go here and then go back and then go back and go here and get stuck in that loop, within the same path, we need to mark these are as visited within the same path. But once we are done from that path, we need to revert it back to 0 so that we can do another path that goes through the same point, right? And so to do that, we can either use a visited set, right? Or we can just mark the value itself with something custom like -2 or -3 or whatever value that is not one of the 3 that we have, so that we don't go through it again, right? So that's the other idea. But the rest should be pretty much just doing DFS. So yeah, that's the main idea. Let's implement it and make sure it passes. Okay, so let's implement what we just saw in the overview. So what we need is, we need to first determine what is our starting position. So we know that starting position has value 1, but we need to get the index so that we can start the traversal from the starting position. And we need to calculate the number of empty cells, because as we said in the overview, we'll need that. And so what we can do is just go through the rows. So basically we need to define what are our rows and columns in this grid. So let's call them rows. Columns are equal to the length of the grid, and the length of the number of columns are that. Now we need to go through the rows, and then we need to go through the columns, and we need to check if this is equal to 1. That means it's the starting position, so we need to mark our starting position. And so we just need to have a variable for that. Initially it has nothing, so here that means ij is 1, and we don't need to break here because we are guaranteed we have only exactly 1. That's what the problem says. Okay, it says it here. There is exactly 1 starting cell and 1 ending cell, right? Now if it's equal to 0, that means if it's different than -1, right, which means it can be either the starting position, the end position, or an empty place that we can go through, then we want to increase empty by 1, right? Because we want to go through all of these, including the starting position and the end position. Now if it's, and that's pretty much all we need here. Now we need to just initialize our count of paths, and we need to start our DFS, backtracking DFS. So let's just call it. What we need to pass it is, of course, the starting position, which is just start 0 and start 1. So that would be ij here. We also need to pass it the number of empties, because remember what we said is we are going to decrement it, and we know when we reach the end and it's equal to 0, that means it's a valid path because it visited every set. And we'll make sure we don't visit a set multiple times by marking the visited cells with a specific value, right? And so here we would have pass empty. But we need to decrement by by 1. Why? Because we just pass it through start, because we are starting from it. So we decrement for that. And then here we return self-dat paths. Okay. And now we need to define our backtracking function. So it takes the starting position, or the position we are at, and then the number of remaining empty cells. Or you could call them maybe non-obstacle, whatever you want to call them, if it's easier. Now we just need to go through the neighbors here. What are the neighbors? So we can go either down one row, or up one row, or we can go left, like this, or we can go right, like this. Okay, and then we call our function with these new values, but we need to decrement by one empty here because we just visited the cell ij. We just, visited the cell in ij, right? So we need to decrement, okay? But here we need to make sure, because we call here and we don't check that these are out of boundaries, we need to make sure they are not here. So when are they not, when are they out of boundaries is if it's not within, I is not within 0 and rows, and j is not within 0 and columns, or if the cell is an obstacle, then we can't go there, so we need to exit. So when is it an obstacle? Is if it's different than -1. So either not within the boundaries, or it's smaller than 0, because otherwise it's either, the valid ones are either 0, 1, or 2. That's what we have here. So 1 is the starting position, is valid. 2 is the ending position, is valid. 0 is also an empty cell we can go through, it's valid. These -1 is obstacle, so we don't want to go through it. So we can just check for less than 0. This would be important also because if we visit a set, instead of using a visited set to mark it, we'll just mark it with -2. And this will prevent going through a visited set again, because we'll just return here, okay? And now the marking of a visited set that we need to do here, remember? And then once we are done, we need to set it to 0. You may say this will mark starting position from 1 to be equal to 0. That doesn't matter because we traversed the starting position just once. We don't need to traverse it again, so it doesn't really matter, right? The only thing we needed for equal to 1 was this here. Okay, so now we want to check if our, if we reach the end. So we can just check if this is equal to 2 and empty is equal to 0, right? So this means we arrived at the ending position, but we also visited every cell exactly once. Why did we visit every cell? Because empty was decremented until it reached 0, and it was initially the number of all the cells that are not an obstacle. But we also won't visit a set multiple times because of this. Okay, so that means here we can increment our path by 1 because it's a valid one, because it visited every cell once, every non-obstacle cell once. And that should be it. So let's run this. Okay, it looks like there is a slight thing here. Let's just, name this M. That's what we used it as. So let's just make sure this is consistent everywhere. Okay, it looks like there is a small error. So let's check where. So one thing we want to do is, by the way, is mark our ending position. So here 2, we just want to do the same thing we did here, end, just to mark it. So let's say, so our end would be equal to ij, and so that it's not affected by this, by the setting here. And so we just check if ij is equal to end, okay? And that should work, right? Because before we were overriding it with this 0. Okay, so now if we submit this, it passes test cases, right? Yeah, so pretty straightforward application of backtracking. And the main idea here is to make sure we visit every set exactly once. Every cell exactly once. Yeah, so that's pretty much it for today's problem. I hope this was clear. Please like and subscribe, and see you on the next one. Bye.